Welcome to Lab 4, Introduction to Seawater Properties. The atom diagram. As you may recall from chemistry, atoms have a central nucleus of positively charged protons and non-charged neutrons, around which negatively charged electrons orbit in a series of orbital or shells. The water molecule. The water molecule results from the covalent bonding of one oxygen atom and two hydrogen atoms. As individual atoms, hydrogen has one proton and one electron, while oxygen has 8 protons and 8 electrons. While a water molecule's covalent bonding technically produces a neutrally charged molecule, the presence of 2 lone pairs of electrons in the oxygen atom and 2 hydrogen ions results in an uneven average charge. This results in a net negative charge on the O-dominated pole and a net positive charge on the H-dominated pole. As a result of oppositely charged poles, adjacent water molecules are attracted to one another. These between-molecule hydrogen bonds, though only approximately 5% the strength of the within molecule covalent bond, are responsible for many of the distinct properties of water. In this lab, we will explore the properties of water in the context of temperature and salinity. Salt. There are many types of salt. For the purpose of this lab, we will focus on sea salt or sodium chloride. The sodium chloride molecule consists of one sodium, a positive ion called a cation, and one chloride, a negative ion called an anion. These two ions are held together in an ionic bond. The resulting chemical formula for sodium chloride is NaCl. Thus, individual sodium chloride molecules tend to attract each other and form what's called a crystal lattice. Hydration. The water molecule is often called a universal solvent because of its effectiveness in breaking or hydrating the crystal lattice to produce dissolved ions. The hydration process may be witnessed by watching table salt dissolve in water. At the molecular level, hydration is where the water's charged poles pull apart the chemical bonds among the individual NaCl atoms, which dissolves the lattice atom by atom to produce dissolved solids within the water. The process of hydration. Sodium chloride consists of positive sodium ions and negative chloride ions in the form of a crystal lattice. Water's hydrogen bond, which is stronger than ionic bonds, pulls apart the NaCl molecules. Water's positive pole attracts the negative chloride ions, while negative poles attract the positive sodium ions. This process is called hydration, resulting in dissolved solids in water. Salinity. Salinity is defined as the amount of dissolved solids in water. The most common dissolved solid is sodium chloride, commonly known as table salt. The total amount of dissolved solids includes dissolved gases, but excludes dissolved organics. The salinity of the oceans average 3.45% by weight. However, this is commonly expressed in parts per thousand, making the average salinity of seawater approximately 35 parts per thousand, or 35 grams of dissolved solids divided by 1,000 grams of seawater. Salinity measurements. In the past, salinity was measured in weight of dissolved solids. A seawater sample was heated to evaporate the water, and the remaining salt residue was weighed. Now, salinity is measured by conductivity using a conductivity meter. Because salt acts as an electrolyte, the measured conductivity of seawater is directly proportional to the concentration of dissolved ions. Later in this lab, we will use a conductivity meter to create a graph called a calibration curve. A calibration curve is used to determine the total amount of dissolved solids. Density. Question: how does seawater density change with salinity? Using the density formula, where density equals the mass per unit volume, salt, or NaCl, is the represented mass, while seawater is the density in question. Thus, if you increase mass, or the salt, then seawater density must also increase. Or more specifically, in parts per thousand, a one parts per thousand increase in salinity will produce approximately a 0.001 grams per cubic centimeter increase in seawater density, or approximately 1/1000th. Temperature, salinity, and seawater density, the concept of isopycnals. Both temperature and salinity affect seawater density. Salinity, on a per unit basis, has at least twice as large an effect on seawater density compared to temperature. However, global salinity levels vary only slightly compared to temperature change. Temperature. Because of the wider range of global seawater temperatures, temperature often plays the dominant role in variations in ocean density. Regardless, temperature, salinity, and density are directly associated with one another. Given the two values of temperature and salinity, density can be determined when plotted on a temperature-salinity graph with isopycnal curves of equal density. Also known as a TSD graph, or a temperature salinity density graph, we can use this to determine the density. We will do this in a future lab assignment. This concludes Lab 4, Introduction to Seawater Properties. It's now time to begin your lab assignment. To assist you, a separate video tutorial is provided for each section. Begin with Video 2, Part A, Determining Salinity and Conductivity Measurements. And please address your questions to your lab TA.